Okay, hey guys. So I just wanted to quickly review Ka and pKa because I noticed that there were a couple misconceptions and misunderstandings on what different numbers mean and how to use it in like a reaction and determining does the reaction go left, right, or is it in equilibrium. So just a quick thing, I'm going to review Ka, what does it mean? I'm going to talk about pKa and how it's used. Understanding the pKa table is very important. It's very useful. You will be provided it on the test, so it's great to know right now how to use it so you can make the most of your time on that exam. There's also the very important pK difference rule. This is how you can tell if it's going to be in equilibrium for a reaction or if the reaction is going to lean towards a different side, which remember, that side will always be the weaker acid. A weaker acid is more stable. We prefer stability in organic chemistry. Chemistry likes stability. So let's start with review of Ka. So first thing you need to know about Ka is that it's the acid dissociation constant. All you really need to know is that it just measures the acid strength by telling you that like it dissociates a certain amount in a solution. So a higher Ka value means a higher acid strength. So you want that number as high as possible. A lower Ka means that the acid strength is lower. So direct relationship. If something's higher, the strength is higher. If the Ka is lower, strength is lower. So here's like a little example, or like actually the way you derive that equation. You don't really need to know this that much, but it's just good to have in mind if you're wondering where we'd get this from. But I do not think you guys will be tested on that. So don't quote me on that, but I'm pretty sure it's not going to happen. So here's a little example. You have Ka1 equaling 500, Ka2 is 20, and then Ka3 is 1 to times 10 to the negative 3. I wrote it on decimal form because I know sometimes scientific notation is a little bit hard to visualize. But yeah, as you can tell, the highest Ka value was Ka1. So it's the strongest acid. The Ka2 is in the middle. It's a higher number than Ka3, lower number than Ka1. Therefore, it is weaker than Ka1, but is actually stronger than Ka3. And then, of course, Ka3 is the weakest acid. So just to do some practice, you can pause the video and try it on your own if you'd like to. Here are the different practice ones you can do. So say which Ka is stronger. Is it Ka1 or Ka2? So I do have some of them written down already. So I wrote them down and what they would look like, not in scientific notation. Once again, probably helps out with visualization. So Ka1 is about 10,000, Ka2 is 1,000. Make sure you do know how to read the scientific notation because we will primarily give it to you in that way, not written out like as 10,000 or 1,000. But we know that 10,000 is greater than 1,000, so Ka1 is greater than Ka2. And since Ka1 is a larger number than Ka2, it is also a stronger acid than Ka2. And so, once again, here is example 2. So now I did it the opposite where you have very tiny numbers. So for Ka1, I don't know what that is, but it's 4 zeros in front of 1 and a decimal point, very tiny. Ka2 is, of course, much larger than that value of Ka1. And since Ka1 is less than Ka2, Ka1 is a weaker acid than Ka2. And now the last one, where I threw some random numbers in there, looks a little bit scary, but once again, it's just looking at which value is larger than the other, or vice versa, which one's smaller than the other. So Ka1 is in fact greater than Ka2. You can just look at the decimal placing. Doesn't matter about the number, if it's 1 or some random number like I showed you. Definitely is a lot larger because if you look at the tens, there's a difference. And so since Ka1 is greater than Ka2, Ka1 is a stronger acid than Ka2. Now, if the numbers were equal, so say for example, you had a Ka1 value of like 1 and a Ka2 value of 1, they're both equal, therefore none of them are stronger. They have the same strength of acidity. Just like a tiny thing you can probably assume from the rules, but yeah. So now let's get into pKa. This is a lot more useful. You're going to be seeing this a lot more frequently than Ka, but it's still important to know the Ka because they could pop up on the exam. So pKa is very similar to Ka, only in the sense that it's also telling you about the strength of an acid. We use pKa because it's a lot more easy to understand. When you have Ka, you have like huge numbers up to the thousands, 10,000, anything, right? Or very, very small decimals. pKa is a lot more restricted. You'll typically see them in less than triple digits. So like -9 or 9. Like, -9 is a very strong acid, 9 is a weak acid. So that's just a lot easier to tell. And also, it's just more practical. But yeah, so here's the equation. This is how Ka relates to pKa. So it's the negative log of it. So here's like an example I wrote down. Say you have Ka is equal to 1,000,000,000. You put that into the pKa equation, and you get out that pK is equal to -9. It is so much easier to read that -9 and understand the strength than seeing 1,000,000,000. It's just, okay, it's a negative number, therefore it's a stronger acid. So yeah. And then here's another example. So say you had a very small Ka, 1 to 10 to the -9. That's a very, very small decimal, as you can see. So you take the pKa and you realize that it's a weak acid because you get a 9. So that's just a general gist of that. So a very important rule, though, this is where pKa varies from Ka, other than the fact that they're not actually the same numbers or anything, but a higher pKa actually indicates a lower acid strength. So remember, when we had a 9 for the pKa, it was a weak acid. That's a greater number than the -9, but the -9 was a strong acid. So that's where that inverse relationship comes in, unlike Ka, where a higher Ka was equal to a higher strength in acid. pK is the opposite. So if you have a lower pK value, like -15, that means you have a much higher acid strength. So you want a lower pK. That's good for acid strength. So whenever you're talking about a reaction, so you guys had this on your homework, and this is kind of why I wanted to make the video, because I saw some people were like misunderstanding how you do it, and it's perfectly fine. This is quite a challenging part of Orgo, I'm not gonna lie. Even though it's a review, it does come up. You do need to know it, so it's good to take care of that right now. So you need to take the pK difference between the acid and conjugate acid only. Notice that the subscript of pKa and Ka are A's. That indicates it's talking about the acid. We don't know anything about the base. There is a pKb and there is a Kb. We know that a higher pKa value is a weaker acid, therefore a stronger base, but that's not what the focus is. Ka is talking about acids. pK is talking about acid. So only look at that acid and conjugate acid. And this will make more sense. I have some examples with the table, and I'll show you why I'm emphasizing acid and conjugate acid only. Just look at those. I'll show you. So first, let me show you how to take the difference. You take the pKa of the acid or the conjugate acid. The order does not matter. So just take the pK of the acid, subtract that from the pK of the conjugate acid, and if that number is less than or equal to, so including the 3, the reaction is at true equilibrium. Now, if you do that difference and you get a value greater than 3, the reaction shifts to the side with the weaker acid. So the higher pKa. You want the side with the larger pK. That will be the weaker side. And that's where the reaction will shift. So this is where the very helpful table comes in. So here is the pK table that you should be given on the exam. I'm pretty sure it'll be these ones. This is like what was given on previous exams. You can always double check with Dr. Berg and he'll let you know. But a general trend, know that the stronger the acid, the higher up it will be on the table. Look at the pKa's. Remember we said a lower pKa means a stronger acid, so -10. That is a pretty strong acid. So higher up you go, stronger the acid. And then the relationship's actually the inverse for a base. The higher up you go, the weaker the base. But then if you go lower, you get a weaker acid. So a pK of 50 is very, very weak. That is a much stronger base though. So that's just the general trend of it. So here are some examples with the reactions. So this one is very similar to your homework, and this is what you'd most likely be tested on an exam. Like this is what you would be seeing. So let's go over this together because I do want to do it step by step. So the first thing you're going to do when you're looking at a reaction like this, determine what your acid and your base are. So looking at this reaction, you can like pause the video here. I'll show you the bottom one as well with the table. Pause the video, see if you can figure it out. If you can't, unpause it and let's discuss it. So which one of these molecules is gaining a hydrogen in the product side? It's the NH3, right? You went from NH3 to NH4 plus. So what do we know about something that's gaining a hydrogen? It is the base. And since that's the base, NH4 is now the conjugate acid of that base. And since we know that NH3 is the base of the reaction, we know that HNO3 is the acid. You can also look at the other side. It lost the hydrogen, meaning it donated that hydrogen away. So HNO3 is the acid. Its conjugate base is NO3 minus. And a way, if you kind of have trouble with visualizing that, try doing the opposite of the reaction now. Read it right to left. So NO3 minus is gaining a hydrogen, hence why it's the conjugate base, because on the product side, it is now acting like a base. The opposite happens with NH4. It is now losing a hydrogen, it's donating it to the NO3, therefore it's a conjugate acid, it's not a base. But yeah, so once you have that defined, now you can actually start using this extremely helpful pKa table. Remember, we only look at the acids, so I only care about HNO3 and NH4 plus. These are all I care about right now. I'm just going to look at their pK values, compare them, and use their values to determine if the reaction leans towards the weaker acid side or it's at equilibrium. So let's look at that. So we have HNO3. So let's look at the table and look at that. HNO3 is right there. And we see its conjugate base, NO3 minus. So their pKa is negative 1.4. Now I need to find the pKa for NH4 plus. So I look at the table and I see that there's an NH4 plus right here with an NH3. So something that trips people up typically is when something appears twice in the table. So here NH3 is present, but also NH3 is present down here. So how do you determine which number, like which pKa am I going to use? You have to have both of the molecule types in the reaction. I have NH3 and I have NH4 here. I do not have NH2 minus, meaning I am not going to look at this side. I am only going to look at that one, the NH4 with the NH3. So the pK in that case is 9.2. So now I'm going to give 9.2 to the conjugate acid. Remember, we only care about the acid when we're talking about pKa. Now, I'm going to take the difference. So, like I mentioned before, the order of subtraction doesn't matter. You can do conjugate acid pKa minus the acid pKa. I'm just going to always subtract it in a way that like we'll get a non-negative number, just so it's a lot easier to show the difference of like, oh, is it greater than 3 or less than 3? So I know that if there's a negative number, I'm just going to do 9.2 minus 1.4. And that's going to become a plus. So that's going to equal 10.6 for the pKa difference. This value is much greater than 3. Therefore, we're going to have the reaction lean towards the weaker acid. Remember, the weaker the acid, the greater the pKa value. 9.2 is a lot larger than negative 1.4. That means the reaction is going to the right. So remember, check first the difference to see that it's not in equilibrium, and then we look for the higher pK value for the lower strength of the acid. So that's how you do that one. So down here now, I threw in water because this one can be an acid or a base. Depends on the problem. In this case, though, it is gaining a hydrogen, therefore it is the base of the reaction. And we know that since H2O is the base, H3O plus has to be the conjugate acid. And so if that's the base, H2 needs to be the acid, and you can tell it lost a hydrogen. So that H minus is now the conjugate base. Remember, we only care about these acids. I just want to find the pKs of H2 and H3O plus. So let's look back at our very handy pKa table, and let's find, for example, H2. Start with that. And there it is. There's H2 with H minus. Both of them are present, meaning the pKa is going to be 35. Now I'm going to want to find H3O plus, and that is up here. Remember, just because there's water down here doesn't mean we're going to be using this. We do not have an OH minus. We only have an H3O plus with the water, not the other way. So the pKa here is negative 1.74. So just looking at this, you can probably tell the difference between the pKa's is going to be much greater than 3, but I'll write it out again. I want to make it so that I get a positive number. You can get a negative. You're just going to have to know like the value when it comes to like seeing if it's equilibrium or not is going to be like x is less than or equal to 3, or x is greater than or equal to 3. So it's a bit weird. That's what I'm saying. Let's just ignore the negatives. You don't have to deal with that. Subtract in a way you don't have to deal with that. So minus negative 1.74. Remember, those two negatives make the positive. You're going to add them, so you're going to get 36.74. This is the pK difference. It is much, much greater than 3, meaning that we're going to be leaning towards the weaker acid. Higher pKa means weaker acid. This reaction is going to go left, just like that. I would recommend doing some practice. I think we have some problem sets available on Canvas that show it. You can also Google it online, say like pK difference, reaction leaning towards, I don't know, weaker acid practice problems. You'll definitely find something. And if you guys ever want more practice, feel free to reach out to one of us and we can do it. But I hope that helps out a little bit more with like explaining how you are going to find the difference and how do you determine which side the reaction leans to. If for some reason we had an example where the left side's like the reactants had a pK of 36 and then the product side had a pK of 37. So like reactants had products as the pK. Remember, only the acids we're talking about. That difference would be 1. That is definitely less than 3. So then you would say, oh, it's in equilibrium. Neither side is favored because their pK difference is so small that their strength, their acid strength it's just hard to differentiate. They're both stable or unstable enough where the reaction doesn't favor either or. So that's basically what's happening with equilibrium. But yeah, hope that helps.